Physical science students, I'm here to talk to you about your lab that we're attempting here. It'd be better if we were in the classroom and actually doing this on our own. If you have some supplies that you want to gather data on your own based on my video demonstrating how to set it up, you can always modify to make your ellipses, but I'll go ahead and do this with my daughter and have her demonstrate how to create your ellipses and go ahead and go through that first process. So as far as your lab goes, we go to the lab paper here. You're supposed to read through. The purpose is to understand Kepler's 3 laws that describe the movement of planets and other objects in the solar system. You got background information, which you should recognize some of those names because yesterday you were supposed to have read through and looked through geocentric and heliocentric models and how those came about as far as the scientists associated with those. So that's kind of like a review of that. And we're going to discover more through Kepler and his laws. Right now, you learned about Newton in first trimester, so now we're going to learn about Kepler and what he did as far as explaining planetary motion. So read over, just glance through the lab and answer these 5 questions. What is the title lab? What's the purpose? How many laws will this lab explore? Compare and contrast heliocentric and geocentric. And you're going to name any the astronomers that contribute to the explanation of planetary motion. Okay, so once you do that, because you should be able to do that by now, and hopefully more of you are participating, I'm having more feedback and people participating with my upperclassmen than my freshmen. Just make sure so that I know that you're doing stuff and turning it in. I'm fine if you mark it as turning on Google Classroom, but please submit through my form because that's how I check to see that I keep record and I have it organized of who's turning in what. I haven't got a lot of the new stuff in that I know of, but I haven't looked on Google Classroom. It's just easier if it's all in one spot. So I know some of you have been sending things through email, and I understand that, especially if it's old work. But I prefer email as communication for questions and help on things, and to submit your assignments through my form and then mark it as turned in on Classroom. The only ones you won't mark as turned in Classroom would be your lab notebook and your online science journal if you're using that. I just sent that to you guys, I believe, the other day. It's up to you if you take notes based on the geocentric and heliocentric from yesterday. If you want like brief key point notes, that's usually what I've been telling my physics students to do when we have notes. So that is up to you. You weren't required to, but you can as far as summarizing what you learned type of thing, or I can always do that tomorrow and have a question and summarize what you learned about them. So with this lab today, you do your background questions, and we're going through the first law. So first law is known as the law of ellipses. It states that all objects that orbit the sun, including planets, asteroids, and comets, follow elliptical paths. An ellipse is an oval-shaped geometric figure whose shape is determined by 2 points within the figure. So kind of like an egg in a way, as far as the outline of the shape, and then the 2 points in the middle are your focal points, plural is foci. Each point is called a focus. At one of those points, though, in the solar system, the sun is at one of those dots, or those focal points. So planets orbit around the sun, correct? So the sun is at one of those focal points, and the second focus is empty as far as what we're dealing with. So what you're going to be doing is you're going to examine this by drawing 3 different ellipses with foci that are different distances. Well, the ones that I decided to give you, and I think I mentioned this on Google Classroom, was the, I believe, I got to look down here. Let me scroll down a little bit. So here's the figure that you're looking at to make your prediction that I'm talking about that I'm going to make, and then we're going to create our ellipses based on that. So you need to figure out or make a prediction on which one you think is going to be the most eccentric. Now, if you haven't done your vocab, which was due today on the vocab, you might need help with what that means. So my hypothesis is that the ellipse with the foci of blank will be the most eccentric and why. So one thing you can do right now, you can say top, middle, or bottom, A, B, C if you want, like saying which foci. But what I'm going to do is you can notice that this middle one's the farthest apart. So I'm going to have that be 8 centimeters apart between. And then hopefully these numbers should work out fine. And then you notice how this one's the closest together as far as those focal points. So I'm going to make that be 2 centimeters between, and then this top one is going to be about in between type of thing, and it's going to be 5 centimeters. So I'm going to go ahead and have my daughter make those 3. But first thing you got to do is make a prediction. So do you think it's going to be the 5, the 8, or the 2? Or you can say top, middle, bottom if you prefer, or A, B, C if you want, just so I know which one you're talking about and explain why you picked it. So to talk about most eccentric, that means it's a measure of the flatness of an ellipse. So the flatter the ellipse is, the more eccentric it will be. If it's more round, it's least eccentric or less eccentric. Okay, eccentric is kind of odd. Think of an odd shape type of thing, or outside the box or different type of thing. So it's going to be more flat. So which one's going to create the flattest ellipse? So that's going to make your predictions on. So you should do that before you see the video that I attach demonstrating my daughter going ahead and going through this. So you can do this at home if you want. It doesn't have to be on computer paper. It can be in any paper. What you'll do is you can make a line if you want, but what I'm going to do is I'm going to tri-fold, fold it in thirds, and then flatten it out so it has 3 different sections. And then we're going to use, you can use any type of string or yarn or something like that to use to set up like this. So this is what I'm going to use. I'm going to use string. These 2 dots here are our focal points. So I use like cardboard. So I have like a gold cardboard shoebox I'll probably use. Or if you have any kind of pieces of cardboard that you're able to use or allowed to use, is usually what I use. And then I have push pins. So like if you have a bulletin board, those type of things, if you have paper clips or something, you can always, I'm trying to think of other things you could use. Just be safe if you're going to use something different. So push those into where those points are on your paper. So I would just map it out with it on the cardboard box, and then I'd push the pins in. And then what I'm going to do is I'm going to pick a string, because sometimes I have different size strings in my box that we would have used, or yarn. And I'll pick one. I got to make sure when I go around like this, what I'm going to do is you pull the pencil out, okay? And then I'm going to go around and pull it tight and make sure it goes around both push pins. And I'm doing this, and I'm going to go around and try to make the ellipse based on where those are at. So I'm just going to kind of go around and make that. So you have to use the string to make this accurate. Otherwise, you can just look at my demonstration or my example and use those values that we have, okay? All right. So looking at figure 1, make a prediction on which one's going to be most eccentric and why. And then I will also make sure I get the data for you, because on the next page, which we're not, we're going to skip over kind of this planet thing. This kind of explains on your paper what these things mean. So it's good to read through that. Okay, so there's explaining more how to do that, what I've just talked about. All right. So the sun's at one of those foci, and the other one's an empty focus. Planet's going around. That's what it represents. Planet going around the sun. All right. The major axis is all the way across. And the minor axis is up and down. So the 2 values of distances you need, which I will already give you, the foci distance, the 5, 8, and 2 centimeters. The distance across is something I will have to measure, or if you're doing it on your own, you have a ruler or whatever, you can measure yourself. All the way across, those are the 2 numbers we need. So all the way across will be after you make your ellipses. I'm trying to think. Oh, the one thing you have to remember when you're making your ellipses, if you're choosing to do this at home and trying this out at home, if you're struggling, let me know if you want to try it at home. I have another video that kind of shows another PDF thing that shows an example of how to make the ellipse besides what's written here and what I'll show in the video. But when you make your ellipse, you want to make sure that the edge of the string or yarn or whatever you're using as material, it could be like bracelet string. I mean, it can be anything that you choose. It just has to make sure it goes around the push pins. Like here's going to be hard because you're going to have a bigger piece of yarn or a piece of whatever you're using to make that ellipse. It just has to make sure it goes around it, and so that you can pull the pencil out, or pencil will be best if you mess up, and then you're pulling as tight as you can and going around and making that ellipse. So you just got to make sure it doesn't go off the edge on the sides, because you have to measure that total length across. So if it goes off the edge, you won't have that value. So just make sure it at least goes up to the edge of the paper if needed. It's okay if it goes off the top, just to make sure you're not drawing on your table or whatever. I put like, I'm going to put, mine will be on a cardboard box. So just make sure if you're on the table or for some reason, push pins don't ruin your table. Don't need your parents mad at me. So make sure you don't go off the edge. It's okay if it goes off the top and on the bottom into the next one. That's okay, because you really just need to make sure you have this distance, which I'll give you, and then you need to make sure you get the distance across if you're able to do it on your own. Otherwise, I'll give you my values, okay? So we'll go around and we'll make that. No, it will go off the top. Same thing here when you make this one. Depending on how big your string is, okay? You don't want it to go off the edge again. You can go up above and down below to make it just big enough to fit around and be able to make your ellipse, okay? And then same thing down here. These are a little closer, so you don't need as big of a string. Doesn't matter. You can maybe use the same one as this one. But this one, you won't be able to use the big string because it'll probably go off the paper. So again, just make sure it doesn't go off the edges. All right, and you'll use this chart later on the next page. So I'll demonstrate that here shortly. You should be able to at least go through the background questions right now and the prediction. And then if you want to start setting up your paper, I'm going to do a video on that to add on of the demo. I'm going to do this thing all together. After you have all that information, it talks about eccentricity out of roundness is how it describes it. It's how much it deviates from a perfect circle. Okay, because a circle only has one center of focus, so the eccentricity is 0. The greater the eccentricity, the less circular it is. Okay, so what you're going to do is, like I said, I'll give you the distance between. I will also, you're going to draw the edges from edge to edge. So once you draw your ellipse, so like for example, this ellipse, I would measure this value here, and then I'd measure the length across. Those are the two values I need. So the distance between the 2 points or foci points would go here. And we can just leave it in centimeters is fine. If you want to convert to millimeters, you would just times it by 10 or move it over 1, but that's fine. We can just leave it in centimeters. And then the length all the way across would go here. And again, it's up to you if you want to convert to millimeters, or we can just leave it in centimeters. And then what you're going to do for eccentricity, the equation is E equals F divided by D. So eccentricity is the distance between the points divided by the total length across. Okay, so you'll just say your 5 centimeters divided by whatever that length across is equal to the value. Now, since you have centimeters for the distance, centimeters for the length across, what's going to happen to those units? Since they're the same, it's kind of like if you have 2 divided by 2. What's 2 divided by 2? It's 1, right? Or if you have 2a divided by a, well, the a's would cancel out and you'd be left with 2. So it cancels out, so you don't have a unit for your answer. Okay, you're going to have something, it should be, note here, it should be between 0 and 1. Your answer should be if it's negative value, or if it's above 1, then you did something wrong. So you might have flip-flopped it. So take your distance between, divide by your total length, and again, I'll give you those values of what I get. And then you're going to look at these values and say, okay, which one's the most round or closer to a perfect circle, and which one's the least round? Remember, most round is going to be closer to 0. Least round means it's closer to 1. So in other words, the roundness is the smallest value, and then the middle one's in between, and then the biggest value will be the least round because it'll be more flat or more eccentric, okay? All right, and that's the part we need to get through with the video demonstration with that I'll do with my daughter. And then after we get through that, which that will take a little bit, you can look at the planet data table on the other page here, and it shows the eccentricity of different planets right here, okay, the E. So it shows Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and it still has Pluto on there, even though it's a dwarf planet. But we have those on there. And so what I would do first is I'd list them in order from least to greatest, like the numbers. It might help you kind of look how they line up. And then you are going to list them out on here from least eccentric, which means closer to 0 or more round, to most eccentric, which is going to be closer to 1. It's going to be more flat as far as this elliptical path. Okay, so you just list those out on there. And then when you're done with that, this is a question based on Kepler's first law. If you don't remember what Kepler's first law, it's pretty much what we're doing. It's called the law of ellipses. It talks about, on the first page here, right here, it states that all objects that orbit the sun, including planets, asteroids, and comets, follow elliptical paths. And then it's talk about the ellipse at one of those focal points is the sun. So think about that law. You can always look back at that. And you are going to answer this question on explaining why the distance from a planet to the sun is typically given as an average distance. So what you need to think about is what happens as a planet goes around the sun, and why is it given as an average distance? So think about that. Okay. The last question for today would be, when you're done with looking at the video, you're going to do the first part here, like I said, through the prediction, and then it's up to you if you want to participate. If you have the supplies or whatever, you don't have to go out and buy any of this or using it, but you have stuff at home that you want to use or just try to follow along. You can try to do this if you want something to do, or you can just follow along with my example. And I will give you these values here, and you're just going to go and solve the math, figure that out, look at the data table on planets and do that and answer this question. And then looking back at your data table, you're going to say, was your hypothesis or prediction supported or refuted? Remember, supported means you were correct with your prediction. Refuted means you were not correct or you were incorrect. So you would say, my hypothesis was supported because, and explain how you know. Or my hypothesis was refuted, and explain how you know, with evidence. Remember, evidence is the values in the statement. So look at your values here. So here's our 3, 1, 2, 3. Ellipse 1 is going to be the top one. So I guess you could have numbered it 1, 2, 3. Ellipses, this is the top, middle, and the bottom ellipses. So I'm going to do that based on the order that it's in on here. So you could say the foci of, you can say 1, 2, or 3, or top, middle, bottom, or the actual values. But this is going to be the first, second, and third one. So based on this, if you think that this is going to have the most eccentric ellipse or the flattest ellipse, then you're going to, of course, explain why up here in your prediction. But then later on, you're going to say, okay, looking at the numbers, was I correct or not? Okay, and then answering that. All right, and that's as far as you need to get for today. We'll go through the second and third law a little bit more tomorrow with some interactives and questions, and we'll kind of gradually keep going through this to make sure you're understanding vocabulary and learning about the laws of Kepler's laws, okay? All right, so I'm going to push pause for now, and I will make sure to have my daughter demonstrate. I think it will be as a separate video as well, based on to draw in the ellipses. It's just easier, I think, that way than using my Chromebook. I'm going to use my phone and upload it to Google Classroom. So I'll go ahead and add this shortly to at least get the first part done, and then I'll add the video of the demonstration here in a little while. Okay. If you have any questions, make sure you always just email me. And I'm on my office hours right now, so I'm trying to get these videos done and make sure you email me if you have questions. Okay. Bye.